Hi, welcome to EC&M Tech Talks. This is a series of how-to videos where we talk about everything from a little bit of basic theory onto the installation and maintenance of our electrical equipment, and even into the codes and standards, certainly, that apply to the installation and maintenance of our electrical equipment. So anyway, this Tech Talk is brought to you by EC&M Magazine, Electrical Construction and Maintenance Magazine. And you can find them at ecmweb.com. So ecmweb.com. And if you have it, you need to go there and sign up for the premium content. So what you do is go to ecmweb.com. Up in the upper right, upper left-hand corner, you will find a little drop-down menu. And the very first item is premium content. Go ahead and sign up for premium content. It's free. And you'll get all kinds of good information and access to lots of articles, videos and so on, and webinars that can help you in all your daily tasks that we do out there in the field. Now, I'm Randy Barnett. I'm your host, your facilitator. My background is I'm a journeyman electrician by trade and got involved in training and writing on electrical topics several years ago, and have been doing that for quite some time now. And so anyway, today we're going to talk about this stuff. So we've got a 100 amp service, right? So we'll imagine this is a 100 amp service. And so what we want to talk about today is grounding. Grounding and bonding is always important, right? So we want to talk about what? Well, let's see. To point out with here. Well, let's talk about, we'll talk about this white wire. And then there's a white wire here that goes out to this MC cable over here. And that's the return wire. We got the hot wire that takes the current out. So this must be the return wire. And I guess this is a grounding wire. Maybe this is the grounding wire here. No. That's not how we talk, huh? If we're going to comply with the NEC, if we're going to read and interpret the NEC, if we're going to be able to talk turkey with people, okay, we all need to be on the same page. And so we need to go to Article 100 of the NEC. I've got the 2023 NEC in front of me today. Article 100 is on definitions. Now, if you haven't looked at the 2023 NEC yet, you're going to notice that all the definitions have been moved up to Article 100 now. So go to Article 100, or if you're using a previous edition, go back and take a look at some of the different articles where those definitions may be, usually in the .2 section. So what are the right terms? Well, first of all, we have power that comes in, of course, from our service. These would be our service entrance conductors. So that means it comes from the utility, doesn't it? And I've got three conductors here. I've got the black and the red, of course, which are not hot wires. Those are our ungrounded conductors because they're not connected to ground. I do have one wire coming in that is white right here in the middle, and that is a grounded conductor. Now, actually, it has black insulation on it, but the code tells us back in 200.6, is it, I think? Yeah, 200.6b. It says that sizes 4 gauge and larger, we can identify them as the grounded conductor at the time of termination by completely encircling that conductor with something white, like white tape, or quite often now you might be using some white heat shrink, something like that. Anyway, so the question is that a neutral conductor or not? Well, I don't know. We need to go look at the utility transformer that's supplying us. And yes, certainly in most cases it's going to be. And what do we mean by neutral? Well, we'd have to go to the code book, Article 100, and look up neutral point and neutral conductor. And yes, we'll find out it is a neutral. Why? Because this tap is in the midpoint between each end, the black and red ends of that single phase transformer out on the pole or on the ground, wherever it is, on pad mounted, whatever, okay? So if I read from right here to right here, so if I read from the black to the red, the ungrounded black conductor to the ungrounded red conductor, I'd get 240 volts on my meter. The midpoint of 240 is 120, right? So if I read from the black to the white, I get 120. Or if I read from the red to the white, I would get 120 on my meter. Now, that makes sense then if I take a conductor, and actually you can see there's a bus bar. So there's a bus bar that runs along behind the red wire and comes down here on the right-hand side, and there's a white wire connected to it. Well, that would also be a neutral conductor or a grounded conductor. The ungrounded conductors, of course, feed through the main circuit breaker into the bus bars. And so my ungrounded conductor would be attached to the circuit breaker. So current would flow in, on this case, on the red wire, wouldn't it? Come on down through the bus bar, go out the circuit breaker, and go out on the black wire. And current would flow out here along the black wire into the load. And then current wants to go back to the source, so it could return back to the source through the neutral wire, the white neutral wire, and of course return on back to the neutral bus bar. And then the neutral bus bar is attached to the neutral on the transformer, so it had that complete path of current flow, right? So that's good. Current's happy. It gets to where it wants to go, okay? Which is always back to the source. Now, keep in mind, though, if we're going to start using terms like return wire and stuff, that gets confusing, because what really happens in this single-phase circuit? Current flows in on the red, goes out here on the black, goes to the load, whatever it is, motor, light bulb, whatever, returns on the white wire, goes back to the source, and then what happens? Current flows in one direction, and it stops, reverses, and flows in the opposite direction, doesn't it? And it does that 60 times a second. So there's current going in and out on these wires 60 times a second then. Now, the insulation for my neutral conductors is going to have to be the same as the insulation of the ungrounded conductors. Let's talk about sizing these conductors. Well, let's talk a little bit first about the rest of the circuit. I've got a green wire down here. Sometimes we call that the grounding wire. That's confusing because they're all connected to ground, or a bunch of them are, except the ungrounded conductors, right? So the green wire, what's the purpose of the green wire? That's the equipment grounding conductor. What the equipment grounding conductor does is, if I have a fault out here, so normally current's going back and forth through the load in the black and the white wires, right? But if something flows into the frame, the metal frame of my equipment, unintentionally, and that metal frame does not commonly carry current flow, doesn't it? So we would call that a ground fault. So we're going to attach this green equipment grounding conductor. We're going to attach the equipment grounding conductor all the way back to the neutral bus bar. Why? Well, think about it. If current flows into the metal frame of my equipment out here, it wants to get back to the source. That's where I'd like to go. I don't want to touch the metal frame of that equipment and have that current flow through my body and back to the source, that's for sure. Okay? So we'll take it through the equipment grounding conductor, and the current will flow back in to the equipment grounding conductor to that same grounded bus bar that's attached to the neutral wire coming off of our service. And the current's trying to get back to the transformer. So where can it go? It can come in on the grounding bus bar from the green wire, go right on back to the service where it's happy again. It goes back to the transformer, complete path of current flow. Now, if I get enough ground fault current, ground fault current, I can have some pretty serious ground faults. If I get enough ground fault current, what's going to happen? The current's going to flow out the ungrounded conductor, flow into the metal frame of the equipment, return to the green wire and back to the source, and this circuit breaker is going to trip. Because basically I got a short circuit, right, into my metal frame of my equipment. Would be pretty common when I have a ground fault. So anyway, I'm going to trip the circuit breaker and clear the fault. That's what I want that green wire to do. It's going to give me some protection. It's going to prevent current flowing through my body and into the ground. That's a good deal, huh? Right? So anyway, we've talked a little bit so far about the ungrounded conductors, the grounded conductor, and our neutral conductors, our equipment grounded conductor, ungrounded conductor. We haven't talked about this guy yet down here. One of the requirements for our service is that this first disconnecting means of the meter, but I'm going to go ahead and I'm going to connect the neutral from the service. And by the way, that neutral, even if I'm not going to use it for some reason, I still have to bring it in from the service. So I bring this neutral in, connect it to the grounded bus bar, and now I take this bare copper wire, it happens to be bare, and I take this bare copper wire off, and it runs out. Actually, I've got it running through some EMT. All we have to do is give it some physical protection. We can run it along the side of a house, but quite often we'll use Schedule 80 PVC, won't we, to give it physical protection. Anyway, I'm coming off a little piece of EMT down here, and it goes over here to my grounding electrode. So this conductor is called the grounding electrode conductor. And what's its purpose? Well, the purpose of the grounding electrode conductor, we can look back in 250.4 in grounding and bonding, and we find out there are two reasons that I connect the grounding electrode conductor to a grounding electrode. And the first reason is to stabilize the voltage to earth during normal operation. If I didn't, and I tried to read, if I didn't have a grounding electrode conductor, and I were trying to read from phase to ground on my cabinet somewhere, or something like that, voltage would be all over the place depending on the load in the system. So it stabilizes our voltage to earth during normal operation. Also, something else very important that this grounding electrode conductor does for us is that it will divert any voltage surges that come through the system into the earth. Well, not all of it. Sometimes we can still get voltage surges downstream into our system. So we see over voltage protection requirements in the National Electrical Code then as well. But let's get back to our grounding then. So we've got a ground rod over here driven into the earth. I can go to Article 250, Section .52. So 250.52 is going to tell me 8 different items that I can use for my grounding electrode. By definition, back in Article 100, the grounding electrode, that's the guy we put into the ground, into the earth. Okay, so there are 8 different types of grounding electrodes that we can have. Now, and I may have more than one. I can have an entire grounding electrode system. That is what we're going to have to install here in a minute, or talk about anyway here in a minute. Okay? And so 250.52 tells me what I can use. How I have to install a grounding electrode, that's 250.53. For instance, on the ground rod, this ground rod is 5/8 inch in diameter. I could get them 1/2 inch, different sizes. But anyway, the larger in diameter my ground rod, then the more surface area I have in contact with the earth, don't I? Just something to think about. But anyway, whatever size permitted by the code, I can certainly use. Now, this is going to dissipate any voltage surges into the earth. My connections have to be made properly. 250.53 tells me that it has to be in contact with the earth for at least 8 feet. Also in 250.53, it'll tell me what happens if I'm driving this in and I hit rocks and I can't get it in. I can put it at a certain angle or dig a trench and bury it in. And all those specifics are covered in the NEC. So, by the way, as these NEC sections pop up along the bottom of your screen, you might want to jot them down or pause the video or whatever and go look things up as you need to. Whether you're new trying to learn all of this NEC stuff and grounding and bonding, or just simply a review for you, whatever it is, take what you need, right? Now, let's talk about how we size some of these conductors and maybe some of the issues we run into. If I take a look in my code book, for instance, I find that 310.12, 310.12 is going to tell me that this grounded conductor can be smaller than the ungrounded conductors coming in. So it's permitted to be that, and a lot of people go, oh, that can't be. Yeah, no, it's permitted to do that. So I can make the neutral conductor right here smaller if I need to, but generally we don't do that probably, huh? Generally, probably make them the same size as the ungrounded conductor. That can become an issue down here when I'm on my neutral wire. I'm running out through some MC cable right here going out to my fictitious load over there. But the neutral conductor also has to carry some harmonic currents, which is another whole topic to itself if I have a lot of digital loads that I'm supplying. And so to carry those neutral currents back, I may have to oversize my neutral conductor in my MC cable, for example. So for instance, I can buy MC cable with the ungrounded conductors 12 AWG and number 10 neutral wire in that same MC cable. Now, as far as sizing the ungrounded and the grounded conductors going out to my load, that's based on my load calculations, right? And whatever it is I'm supplying, I have to look at, the 100% of non-continuous and 125% of continuous loads and things like that. Whatever it is that rules that I'm following there for determining the size conductors that I need for my circuit. Some tables for sizing these conductors. Let's take a look. I want to take a look at table 250.66. And 250.66 is the table that says 250.66. And this hasn't changed since several previous editions of the code. So you're still okay whether you got the 2023 code book or not, okay? It says grounding electrode conductor for alternating current systems. Grounding electrode conductor, remember? That's the one we went from the grounded bus bar down here to the grounding electrode system. Now, it looks at the size of the largest ungrounded conductor or equivalent area for parallel conductors. So my table tells me that for 2 or smaller, and these are 4 AWG, okay? So they're smaller than 2 AWG. It says that the 4 AWG conductors coming in for this 100 amp service, then, according to the table, if I use copper, my grounding electrode conductor can be a 8 AWG, a number 8, in other words, going to my grounding electrode. Pretty simple table. Now, there's another table that we're going to use for sizing. Well, let's go take a look at it because it's several different things. It's table 250.102C and table 250.102C1. We use it to size the grounded conductor up here. We use it to size the main bonding jumper. Main bonding jumper, that's that green screw right there. We'll talk about it a little bit. The system bonding jumper, we don't have a system bonding jumper in here. Why? Because it's not a separately derived system. Okay? If it's a service, it's a main bonding jumper. If it's separately derived coming from another source, say we own the transformer, typically a lot of commercial industrial applications, right? Then in that case, we're going to install a system bonding jumper. And the supply side bonding jumper. Well, we don't have the supply side bonding jumper in the service either. We'll take a brief look at some of the requirements for separately derived systems as well. Now, the difference between the 250.66 table and the 250.102C1, when you first look at them, you go, well, they're the same table. What's the difference? Why didn't I just put? No. If we go and we look for the grounding electrode conductors, we get into some big systems now. Now we're talking maybe some commercial and larger systems, industrial applications, where the ungrounded phase conductor coming in is over 1100 kcmil. So we might be bringing some in parallel, right? Over 1100 kcmil, it says the grounding electrode conductor down here going to the grounding electrode, it says that's a 250 kcmil, okay? That's our largest grounding electrode conductor we're required according to the table, 250 kcmil. Big system, obviously. Now, if we go over and we look at sizing our grounded conductor, okay, our grounded conductor then coming in, and the main bonding jumper, I come down here and the table looks, it says 2 or smaller, number 8 copper, everything looks pretty much the same until I get down to this over 1100 kcmil. When I get down to over 1100 kcmil now, it says C notes 1 and 2. Uh-oh, didn't give me a number then, does it? Oh, note number 1 talks about this 12.5% rule. And so maybe you've heard of that. It says, okay, so if we're larger than 1100 kcmil, copper, the grounded conductor or bonding jumper shall have an area not less than 12.5% of the area of the largest ungrounded supply conductor or equivalent parallel conductor. So you got to read that one, right? You're going to have to study that one do a little calculation there if you get involved in that. Chapter 9, table 8, right? Has all of your areas for your different conductors and your circular nil areas and all of that. Now, the equipment grounding conductor down here, the green wire. The green wire, equipment grounding conductor, okay, if you think about it, we said that the circuit breaker is what's going to interrupt the current flow in the event of a ground fault, right? As the current flows on the ungrounded conductor, goes into the frame of the equipment, which we don't want, of course, returns back on the equipment grounding conductor, the green wire down here, goes back to the transformer. The circuit breaker trips and clears the fault. So what size do we want the green wire, the equipment grounding conductor? Well, let's see. It's protected by the circuit breaker. So why don't we size the equipment grounding conductor based on table 250.122, which is based on the size of the overcurrent protection. So for instance, we go to table 250.122, and it says minimum size equipment grounding conductors for grounding raceway and equipment. For a 15 amp circuit breaker, which is what this is, it says that the copper 14 would be my minimum size equipment grounding conductor. Some other sections here. It doesn't have to have green insulation on it, does it? For instance, in type NM cable, not just Romex, right? But it's type NM cable in the code book. On the type NM cable, it's going to be bare copper. So we may have bare copper green, or we may have green with one or more yellow stripes on it. That's all covered. You see back here, 250.118 is types of equipment grounding conductors. So I can use things like conduits, metal raceways, can I? For my equipment grounding conductor. I may not have to run the green equipment grounding conductor in this case, or a separate wire type, we would call it, equipment grounding conductor. 250.119 talks about identification of the wire type equipment grounding conductors. And then 250.122 gets into the sizing of our conductors. It also talks about, in a case where maybe you had to upsize the phase conductors, because of voltage drop, it talks about a need in there as well to upsize the equipment grounding conductor, something that's easy to miss when we're doing installation work. So we've talked a lot about the conductors. Let's talk about this jumper up here, the main bonding jumper. Right now, the main bonding jumper is screwed in. When we buy the panel, it's already sized. 250.28 has all the requirements for the main and system bonding jumpers in it. So right now, if I were to try to read resistance, right, between this bus bar, the grounded bus bar, and the metal frame of the equipment, my meter beeps. I get 0 ohms. Why? Because that green screw is screwed in, connected to the cabinet. So when I put one test lead on my connector right here from my MT, which is screwed into the cabinet, and touch the bus bar, my meter beeps. I get 0 ohms. The same is true here on the left. And if you look at the construction here, you can see that the bus bar goes across the top and ties into a bus bar on the left as well as the right-hand side. If I were to unscrew the green screw, I wouldn't have the connection now, the continuity between my metal frame of my enclosure and my neutral bus bar then. Okay. So 250.28 talks about the main and system bonding jumpers. And then finally, 250.30 talks about separately derived systems. So the difference, go back to your Article 100 definitions then. And basically, if we come from the utility, it's a service. That's what it is. If power comes in from the utility, it's a service. If it comes from our transformer on site, which is, of course, very common, then we refer to it as a separately derived system. Why? Because we're deriving the power from where? Separately from our own transformer for our system. And so our rules are very similar, but they're a little bit different. Okay? So we talked about, instead of the main bonding jumper, we have a system bonding jumper. We also have to run a supply side bonding jumper that's going to run from the source of, actually from the enclosure and that source, typically the transformer then, let's say, or could be a generator, and it's going to carry that continuity onto the enclosure where that first disconnect is going to be. So kind of in a nutshell, that's how that works. Okay, so we have supply side bonding jumpers, system bonding jumpers, and the big difference between the separately derived system and the service is whether or not we break the neutral. So if we go through a transfer switch and the neutral transfers from the utility over to the generator, then it is a separately derived system. And so we're running out of time now. We're well into it. But anyway, we want to go ahead and close things out. So remember, this Tech Talk is brought to you by EC&M Magazine, ECMWeb.com. It's part of the portfolio of Endeavor Business Publications. And above all, when you go out of here, as always, remember to work safely.